Today I will talk about our recent work on the cloud-empowered privacy-preserving data aggregation for mobile crowd sensing. And this is a joint work with my colleague Mengyuan Zhang and Shibo He from Zhejiang University and Ming Li from UNR and Junshan Zhang from ASU. All right. So recently, we know that the mobile crowd sensing is very popular and has enabled many good applications by leverage the sensing capability of the mobile devices of users. For example, it has been leveraged for the surveillance, the smart transportation, indoor localization, and noise level monitoring. And this is just several applications. And one important issue in the mobile crowd sensing is how to incentive users to participate in different kinds of application tasks. Because the participation is costly in terms of the power consumption, CPU, memory, and disk usage in the mobile devices. And also, recently, people find out that the privacy issue is also a very important dimension we should look at it. And to protect people's privacy, recently, excuse me, recently we can have two kinds of methods. One is protect user by the platform. Say we assume the platform is trustworthy, so people submit the data to the platform and allow the data to be perturbed by the platform before it disclosed to the public. And this kind of method is very costly for the platform. And another kind of method is like the game theory kind of work. And this is, has a very fundamental difference from the platform approach. So basically, it allows users to add noise by themselves. And the noise is kind of negotiated with the platform. But the problem is that since the result is kind of the equilibrium of the result of this game, the platform cannot control the accuracy of the data. Okay, so user will add noise without any control. Okay, so to address this issue, I mean the game theoretical model. So we propose a new framework by not only allow each worker to protect their data privacy by adding noise, but also we let the platform to choose a specific set of users to enhance the accuracy level of the aggregation result. So this is the main research question we answered in this talk. Okay. So here is a basic overview of the crowd sensing framework we propose. So basically, we leverage an auction framework. So we assume that, okay, in this system, we have a task agent, okay? And the task agent will post a task to the crowd sensing platform and let the crowd sensing platform to select worker, okay? And in this framework, the platform is assumed to be an auctioneer, okay? And each worker is to be a bidder, okay? And when the task agent posts a task to the platform will collect the bid from different workers, okay? And based on the bid, the auctioneer will allocate the task to different workers based on their bid, okay? And the selected worker will become the winner in this auction framework and will receive payment of fulfilling this task. And then these winners will send the sensing report back to the auctioneer, okay, which is equal to the sensing data plus noise here, okay? And this is a key difference between our framework with the existing auction framework, which assumed all the user will send the true sensing data, okay? And after receive all these noisy sensing report from the winner, the auctioneer will do the data aggregation and then send the aggregation result to the task agent. Okay, so this is the basic framework of our crowd sensing task. Okay, so in the crowd sensing auction, so we basically consider a data aggregation model represented by this formula. So we consider basically a weighted sum of user sensing report. So here F is the aggregation operation, okay, and D is the sensing data we collect from the user. D is a vector, okay, and we do the weighted sum. Here the WI basically represent workers' diverse skill levels, okay, and a work with a high skill level, the WI will be higher. So this is something used in the MobiHoc in 2016 and also in other papers, okay? And here NI denote the noise, okay? They denote the noise generated by the worker. And XI is just indicate if this worker I is selected or not, okay? And to ensure the privacy, the data privacy of the user, here we leverage the celebrated concept of differential privacy. The basic idea is characterized by this formula. So the basic idea is that, okay, given the data vector D, we can change the value of one component in this vector. After we change it, the output of this aggregation is very similar to the original one, okay? And the difference is bounded by the small factor epsilon I, which is bounded by this epsilon exponential epsilon I, okay? So this is the basic idea. And a well-known method to provide this kind of differential privacy is by adding a random noise drawn from a Laplacian distribution, such that the sum of the noise here follows the Laplace distribution. If we can satisfy this condition, we can say this operation is differentially private. Okay, so this is a basic setup. Here you can see that, okay, this noise is the sum of all the users' noise. Okay. Therefore, there's a so-called externality in this framework, because the noise not only depends on each worker's specific noise, but also the other worker's noise. Okay, and which makes this problem quite different from the existing work. And in this work, we are trying to develop a mechanism to take into account this externality effect and design an optimal way to do this auction. Okay, and later I will discuss what this optimal mean. Okay, and one thing we should notice that as we allow user to add noise, okay, the noise, the sensing data we collect from the user will not be accurate, okay, because of the noise, right? Basically, to reduce the accuracy of the result. And here we introduce this definition called the distortion. Basically, it quantifies what is the expected deviation from the true result and the noisy data. Okay, so the first part here is the sensing data. Okay, so this is sum without noise. Okay. And the second one is the noisy sensing data, right? And the difference is basically the deviation, okay? And we take the expectation and take the max internal data to quantify what is the maximum expected deviation, okay? And under the data aggregation operation in our framework, we can actually prove this, that the privacy of each worker is actually can be quantified by this guy, okay? And this is a corresponding distortion of this data aggregation operation. And from this expression, the epsilon I, you can see it not only depends on user I's parameter, but also the other user's parameter. This is why we have the externality here, okay? And when we do the optimization to select which user to fulfill the task, we need to consider this effect, okay? And in the task allocation, we assume workers' utility follow this specific form. The first part, PI, denotes the price or the payment each worker I receive, okay? And the worker's bid is denoted as BI, okay? And the VI is basically worker's intrinsic valuation, okay? And their difference is the worker utility, okay? And under this model, we want to design incentive mechanism such that we want each worker to truthfully bid her bid, okay? And basically, this corresponds to the first bullet, okay? So if user change their bid to something different from their true bid, the utility it receive, the worker receive will be lower, okay? And the second important objective is individual rationality. So we assume that each user's utility is non-negative, okay? And the third bullet is the cost minimization. We want the mechanism to minimize the total payment to the worker, okay? And the last one is the computational efficiency. We want the result can be calculated as fast as we can, okay? So all these four bullets will be the design objective in this talk. Okay, so under this design objective, we formulate this problem, the crowd-sensing auction problem, in this way. So basically, we want to minimize the total cost subject to the individual rationality, accuracy requirement, and worker selection. Okay, here we add the accuracy requirement to make sure that the result you receive is useful. Okay, instead of letting user to add arbitrary large noise, okay? So specifically, this problem can be formulated in this way, okay? So we minimize the sum of the payment subject to PI larger than equal to BI epsilon I, basically is the individual rationality based on the utility model we propose. And the second constraint is the delta X less than equal to the capital delta, which is the accuracy requirement. So capital delta is something the platform can specify based on the application, okay? And the last one is xi. Xi is the integer, okay? You can either choose the worker to be winner or loser, okay? And unfortunately, this problem is NP-hard. Actually, it's easy to show that this problem can be reduced to a reverse binary knapsack problem, which is NP-hard. Therefore, we need to study how to efficiently solve this problem, okay? And still, we want to achieve all these four objectives in the previous slides. Okay, so here is the incentive mechanism design, okay? So basically, we propose a differentially private data auction. And this auction, basically, we have two main components, winner determination and payment determination, okay? And in the winner determination, the key idea is that we want to find the smallest set of workers that can have the cost as close to the target cost. Here, target cost is given by the solution of the fractional relaxation of the crowd-sensing auction problem. So remember, the crowd-sensing auction problem is an integer program. So we first relax it, and after we relax it, we can solve it, okay? Because it becomes a convex problem, okay? And we want to find some a set of workers such that the cost under this set is as close as to the target cost. Okay. And then we do the payment determination. So once we find the winner set, okay, then we trying to find the critical bit such that a user will become a winner. Okay. Then based on the critical bit, we determine the payment to each user. Okay. So here is the basic idea. Okay. All right. So in the winner determination, okay, so how to find the target cost? Okay. So first of all, we first do the relaxation. Okay. Then we transform this problem from left-hand side to the right-hand side based on the properties that at the optimum point, this pi larger than bi epsilon I is tight. So this constraint is tight. So we can take get rid of this pi. Okay. So this problem actually becomes a linear fractional problem if we substitute the epsilon I and the delta, which we have figured out in the previous slide. And this problem is a linear fractional problem. Okay. And for linear fractional problem, we know that we can find the optimal solution. Okay. Okay. But still, it does not help to how to find the smallest set of workers to have a very close total cost to the optimal one. Okay. Then we further, based on this target cost, we transform this problem into this form. Okay. And they are equivalent, but for this one, it has a very good property we call hidden monotonic property. Okay. And based on this property, we are able to find a set of winner. Okay. So let's look at this algorithm. So the idea is that we first order all the workers bit, okay, in an increasing manner. Then we solve the target cost by using some solver, for example, Cplex, okay. Then we gradually add the worker based on the increasing manner of this bit, okay, until we find some cost is close to the total cost, okay. And then we determine the payment by finding the critical bit by remove each user I and then run this winner determination again, which will give you a bit that can make a worker not a winner. And then we do it for each worker, and then we choose the supreme of all these smallest bits as the critical bit. Okay. Then we determine the payment based on the critical bit. Okay. So this is the basic idea. And we can prove that, okay, this approach, this algorithm is truthful, individual, rational, and also it has a approximation ratio with respect to the optimal value, okay, which is quantified by this expression. Okay. So due to the time limit, I will not go to the details. And after we design the task allocation, we need to find some way to aggregate user's data. Remember, each user will add noise locally. Okay, add noise locally. So we need to find some way to combine these different random noise together such that the sum of them is equal to a Laplacian noise. Okay, and this is done by this one. Okay, so we design each noise Ni equal to the difference of two RID random variable which follow the gamma distribution. Okay, and then let each user to report this noisy report, and we can prove that actually this will guarantee that the aggregation operation is epsilon differentiable private with respect to each worker. Okay, and this is based on the divisible property of the Laplace distribution. Okay. So in the end, let's look at some numerical examples. So all right. So I will quickly go over that. Okay. Thank you. So here is the first example. So we have privacy and accuracy. So we compare the privacy of the user under different normalized distortion. Okay, under different number of users. Here you can see that as the number of distortion increased, the privacy improve, which is expected, right? Because basically we allow user to add more noise. Okay. And here is another example about the externality. So we examine the total payment on the different number of users. And basically, we can see that as the number of users in the system increase, the total payment increase. Okay, and also as the number of users increase, the number of winners increase in this in our framework. Okay, so next we examine the truthfulness of our problem, our framework. So basically, here the red one denotes the critical bit. So we can see that as long as, okay, your true evaluation is here, if it is larger than the critical bit, so you will not be a winner. And if you perturb it, okay, so make it less than the critical bit, although you will become the winner, but your utility becomes negative, okay? And if you are winner originally, and when you play with your bit, your utility will not change, okay? So this is this shows that this mechanism is truthful. Okay, and here we also show the computational complexity. So basically, it's increased with n, but you can see that its running time is very small, about 0.1 second. Okay, for different cases. Okay, all right. So here the last one is about the approximation ratio. So you can see that on the different cases, approximation ratio is around 2. Okay, and this is done by running multiple, I think hundreds of experiments for each case. Okay, so here is the conclusion. So basically, in this study, we propose a new privacy-preserving data aggregation framework that we can allow each user to report a noisy data, and also guarantee that the accuracy of the result is bounded, right? And one thing I would like to mention is that in our framework, we cannot guarantee the privacy level of each user, right? Because this is basically governed by the platform, because platform can select a specific set of the worker, and such that some workers' privacy can be very, very bad, although the privacy loss is compensated by the platform. And in some cases, remember, some users may be very sensitive to this and may not willing to participate. So in the future work, what we plan to do is that we can add some constraint on the privacy each worker would like to achieve. Okay, and we have been done some initial